Good morning. Am I audible? Good morning.
Yes,
Okay, okay. Sorry about the delay. There is no power in the campus. I hope the battery will stand in. Let's see. We are at the end of discussions on C++. I'll do the concluding session now. And we will discuss about probably the most important and most efficient component of C++, that is the standard library. And specifically, I'm not going to discuss about general standard library components like IO stream, which is for input output, or different C standard library which are available in C++ as well. But I'll specifically focus on the STL. STL stands for Standard Template Library. Now you have learned all the required features of the language to understand what a template library is. So I will take you through the certain features of the C++ standard library. I hope the presentation is visible, right? Is it visible?
yes, sir.
Yes, sir.
So I'm using a presentation which is from the website of Strauss-Troop, the creator of C++. So I lifted it from there, and I'll be using that to discuss the C++ template library. So there are a couple of things to discuss. First, let us try to understand why the template library is important. So while we are naturally talking about a very powerful tool like C++, which can be used for any kind of software development in a very structured way, in an object-oriented manner, following all required principles of software engineering, and a absolutely wide range of tasks may be performed. But at an algorithmic level, at the coding level, we see that there are certain tasks which are more common than most others. And the common tasks usually take most of the code, most of the program. So for that, the first thing we will often need is naturally were when you got started in programming, you learned the importance of data structures. So collecting data into containers is certainly the most fundamental requirement. Organizing the data for printing, for fast access, is what is critical. Then we have the requirement of retrieving data items. And there could be several ways that we might want to retrieve data items: by index, that is nth element in an array, this kind of, or by value, say first element with the value chocolate, by matching that, or by certain property, say get the first element where age is less than 64, something else. So retrieval is a key area. Then certainly we need to add new data, we need to remove data, and often we need to do other tasks like sorting, searching, simple numerical operations, and so on. So these tasks are very fundamental to algorithms, to program design, and as well as to software observations, software projects. Now, we can already write programs that are very similar, independent of the data type used. We discussed this aspect while discussing about templates, that using an array, using an int, is not that different from using a double, or using a vector of int isn't that different from using a vector of string. So based on this, we can set out certain ideals as to uh, could we write common programming tasks so that we don't have to redo that work every time for finding a new way of storing the data, or slightly different way of interpreting the data, and so on. For example, finding a value in a vector isn't all that different from finding a value in an array. I mean, conceptually, I'm saying, think of this conceptually. That is the details. I mean, the devil is in the details, and that come in when we get into the specific codes. And we want to set ideals that can we take out this commonality and abstract them in a way so that we can achieve a easier, better, more reliable programming. So the ideal requirement would be we want to generate code that is easy to read. Readability is very important because that is the key factor of knowledge transfer in any software project. It should be easy to modify because change is a persistent reality in software development. It should be more and more regular to look at. It should be short so that there is less to review and less to write and less to debug. And certainly it must be fast because efficiency is a key. So these are certain features of the code that we will expect to meet. And the access to data should be uniform, independent of how it is stored, whether it's stored in a array, vector, list, or some other way, say in a binary tree. And we should be able to uniformly access it independent of its type. So when we are talking about template, we are primarily talking about the second aspect, that how can we access data independent of its type. But in ideality, we would like to also have uniformity of algorithms so that the access could be uniform independent of the actual storage. It must be type safe to access data. We have talked several times about the importance of type safety. For example, when we discussed macros vis-a-vis inline functions, we highlighted that the macros are not good because they do not give you type safety. So type safety has to be ensured. It should be easy to traverse. It should be compact to store because we would want the memory footprint or the disk footprint to be as small as possible. And speed, it should be fast for retrieval, addition, and deletion of data. And on top of this, we would want standard version of most of the common algorithms. We should not require to write the common algorithms every time we go to a development situation. So we saw some examples of sort, but we'll see it from more fundamental perspective. So I mean, just a random list of some common task examples: sorting a vector of strings, finding the highest temperatures, sort the telemetry records by timestamp, or find the first difference between two sequences, and so on. I mean, just to illustrate that there are a variety of problems apparently, but they have a significant commonality of tasks which can be abstracted in terms of this library. Right? We are on slide 8. Now we're going to slide 9. Now, this requirement of being able to write common programs for multiple tasks, multiple data storages, is known as generic programming. That is, you generalize the algorithm to work for different data structures, different situations. And this is also called sometimes as lifting an algorithm. The aim naturally is to increase the correctness through better specification, greater range of use. Reuse, as I mentioned, is a very, very fundamental requirement of software engineering, and certainly better performance by wider use of tuned libraries. Libraries are written by experts and have been used by millions, and they get tuned in the process. If they don't do well, that those libraries get thrown away, and more efficient libraries come up. So getting to this abstraction is important to restrict the code bloat and the consequences of it. So let's just take a look at some concrete algorithm to understand this lifting process. So suppose we want to write a function which will sum the elements in a container. say the first code shows that I have a array of doubles, and the size of that array is n. And this is the code we will write a for loop. You all know from PDS itself, have a local variable s to accumulate the sum. And this is how the sum can be computed if the data is stored in an array. Instead, if the data is stored in a list, so struct node is basically a list node. So you start from the first node in the sum, and again you have a local variable to accumulate the sum. You keep on traversing the list and accumulating the sum total of the elements stored there, first pointer data. So you can see that this is an algorithm that sums the double values in an array, and this is a code that sums the int values in a list. Those are two concretely different code, has to be separately written and debugged and everything done. But conceptually, what you're saying that I have a collection of data and I want to go over all of them and I add them and get the sum. So the next slide, slide 11. So can we abstract this data structure? Can we see what is the core of it? The core of it is I want to do the sum where there has to be a variable s to accumulate the sum. But the basic process is I continue till I have exhausted all the data. While I'm not at end, what do? I get the next data value, add it to the sum, accumulate, and go on to the going to the next data element. And I keep on doing this till there is more data to work with. So we can see that in an abstract way, there are three basic operations that I need on the data structure. That is to check that I'm not at the end, not at end. That is, there should be a way to get the value, current value that I'm looking at, and go to the next data element. Right? Both the array of doubles and list of integer has to support this to be able to compute this sum. Right? So in the next slide 12, I write it in terms of a templatized form in a little lifted manner to say that I have a template of class of a type iter. We will standing for iteration or iterator, which should be an input iterator. We will explain what iterators are really. And then I have a type T, which is the element type, the accumulated type, the value that will accumulate or the elements that will add the type of that. So what sum has to do, it has to have a pair of iterators. That is kind of telling you that this is where you start and this is where you end. And a variable s of type T where you accumulate the value, and then you finally return that variable. So in that process, I can write it as while first is not equal to last. This is what I intend to write. That is, the first and last are two markers. So as I progress over this iteration, I keep on moving the first from the current position to the next, which in case of an array would be going to the next index. In case of a list, it will be doing getting first pointer next. But conceptually, I want to go to the next position on the data element. So this is getting the next data element. And then I can say that the current data element, which is marked by first, I want to get that data element. So I use a star. So three operations, as you can see, that this is not at the end is basically specified by the fact that the beginning at the end, first and the last are not same. Getting a data element is kind of in a notation looks like pointer dereferencing. So it's a conceptual pointer dereferencing. And then you have a pre-incrementer, which takes you to the next element. Right? So if I have this template function, This is a template function, as you know already. Then I can do the sum of this array A and find the float value from it. So what I have to pass to the sum, the first beginning of the iteration, which is A, which is the address of A0, the first location. Then what I pass is the A plus, this expression means the number of elements. Size of A is the whole size of the array. Size of star A is the size of an element. So if I divide, it's the whole total number of elements. So I add that number of elements with A address. So this is a pointer addition, as you can understand. So what it does, there are 8 elements. So the array will go from A0 to A7. So this will do A plus 8. So it is actually pointing to the 8th element, which actually does not exist, right? So it is one beyond the last element. So this is the beginning of the iterator, this is the end of the iterator, and then you pass D, which is the initial value of the accumulated sum that you want to use, which you have initialized to 0, right? So you have now tried to write this algorithm in a lifted manner, where you really do not need, you will not need to write the specific code of how you go to the end or how you get the element and so on. Going to the next slide 13. This is kind of the way the standard library will accumulate values. And this will work for arrays, for vectors, for lists, for streams, and so on. And as it happens, it runs as fast as handcrafted code. Of course, it uses a heavy, decent amount of inlining, the inlining feature of the compiler. The the code's requirement on its data has become now explicit, and we can understand the code better because you are saying it in a more abstract manner. So that is the fundamental of STL, the template library. It is a part of the ISO C++ standard library. As I said, standard library has other components as well, but almost every component use some STL or other in a way. STL is mostly non-numerical. It mostly does computations without numeric operations, except there are 4 standard algorithms which do computation, like accumulate, inner product, partial sum, and adjacent difference. Otherwise, it is actually a mostly non-numerical data that you work with. And one second. So it has handle to textual as well as non-textual data, as well as numeric data. Like it could handle strings, and deals with the organization of the code and data, built-in types, user-defined types, data structures. All of these are looked at by STL. And a great thing about STL is it is highly optimized in terms of disk access, because disk access is one of the costliest operation in terms of executing a program. So performance is the key of this. Historically, this was STL was designed by Alex Stepanov with an general aim of producing a most general, most efficient, most flexible representation of different concepts, ideas, and algorithms. Like kind of his thought, and that has prevailed very significantly with efficiency, is that program is kind of maths. So you should be able to make it more and more mathematical, and that will lead to better programming. Okay, now let's come to the core of it, the basic model on which STL works. So if you look at this abstract generic level, then in any computation you have two kind of things. One is, on one side you have algorithms, And we are talking about common tasks. So there are a number of common algorithms, like you want to sort, you need to find, you need to search, you need to do copy, and so on. Now, on the other side, you have containers which contain the data, which store the data. They can be stored as vector, as list, as map, and so on. Now, the basic problem of low-level algorithm is when I write a code, I need to know the algorithm, and I also need to know the container. So a sorting, like the accumulation example you saw, you need to know about the accumulation algorithm, going over, adding the value, and so on. And you also need to know that it is on an array or a list to be able to write that code. Similarly, so the basic problem of abstraction is that algorithms and containers are intertwined in the code that you write. So the first objective was to separate these concerns, separate these two out. That is, algorithms manipulate data, but they should not need to know about the container. They should just be able to do the task that the algorithm demands. At the same time, containers store data. They should not be concerned about how that data is used or what the algorithm is getting applied on. So these are two sides, algorithms and containers. And in between sits a connecting component through which algorithms and containers interact. They are called iterators. And each container has its own iterator types. Right? So let us look at this in. So uh, the ISO standard framework has about 10 different containers. You should know about these. And about 60 algorithms connected by iterators. Right? Just have an idea of a few. I mean, you can look up the rest as and when required. It's not possible to remember 60 algorithms in the STL. Uh, other than STL, there are extensions that specific organizations use. There are more available in Boost project or in Microsoft's own implementation of STL and all that. We are not talking about those. We are just talking about the standard C++. I'm sorry. We are on slide 19, and we are taking a look at the iterator. So a pair of iterators defines a sequence. Right? So there is a beginning which points to the first element if there is a first element. And there is an end which points to one beyond the last element. I was mentioning in that array that the end is the 8th location. So you can see in the diagram here, begin points to the first element and end points to one beyond the last element. Do not interpret these arrows to be anything. Do not interpret them to be doubly linked list or anything. They're just saying that this is the order in which the iterator will go. In fact, it might iterate on a container which is not a linear data structure. It could be a non-linear data structure like tree. So an iterator supports 3 basic iterator operations. The plus plus, the prefix operator plus plus will take the iterator to the next element. Star, the dereferencing operator, will get the value from the iterator. Wherever that is pointing to, wherever it is marking to, you'll get that value. And the equality or inequality operator will check if between two iterators, if they are pointing to the same element or they are pointing to different elements, right? So this is the generality, this is the abstraction where we saw in the accumulation example. And in concrete code terms, the iterators will use these 3 operators always. In addition, some iterators may support more operations like decrement like addition, like array indexing and so on, but that's not the common part. So let us look at how the iterators will look like. So if it's a vector, then it's necessarily a contiguously allocated sequence of elements. So the begin iterator points to the 0th location, and the end iterator points one beyond the last location. Right? If it's a list, say doubly linked list, now, so it points, the begin iterator points to the first element, and end iterator points to the one beyond the last element, which actually the element does not exist. Say a set is another data structure which is there in STL, which is kind of stored in a tree to do the find operation efficiently, because you will, in a set you will often need to find the membership, whether an element exists in the set. So it's kind of a binary tree, and this is the beginning of this, and this is the end of this. You can figure out from the tree and the positions of the iterator that if I do a depth first, left child first strategy, then this is the node. I mean, the numbering of the nodes are actually based on that. So this is the node that I traverse first, then this, then 2, then up there, come down to 3, and so on. So if you do that traversal, then that order is the iteration order. So this is the first iterated 0, and wherever 8th would have been if it were there is the end iterator, right? So it is always a kind of a conceptual sequence which is closed on left, that is on the beginning, and open on the right, that is at the end, right? So with this, now you can write the iterator. Say I'm trying to do a find, and I want to write an algorithm for find using this iterator. I'm sorry. So what does find need to know? Find need to know the two iterators, the beginning and the end. So we're saying that in is some input iterator type. So I have one iterator which is first, and the other one which is the last. So this is the beginning, and this is the end that we can see. And then I pass a value of type t, which is the value that I want to find. So this is my find algorithm. Simple in iterative terms is a find algorithm. That is, if first, as long as first is not equal to last, because if first becomes last, then you have reached the end. So there is nothing more to find for. So if first is not equal to last, and the content of first is not equal to value, that is, I haven't found the value at the current position, then you go to the next element, plus plus first. So this will keep on continuing. So if the value exists in the container, then at some point this condition will fail and I'll come out, and whatever is the first iterator at that point is the location where I have found the value. Do not think in terms of index or list position. It could be anything, but this iterator will tell you this is where I have the value. So star first will give me that value. If the element does not exist in this, in the container, then the second condition will never fail. So the first condition will fail when I've exhausted doing the iteration by plus plus first. And then what will come out is the value of the iterator, which is equal to the value of the last value of the beginning iterator, which is equal to the value of the last iterator, because that is the condition it has violated. So if I want to find a vector, an integer in a vector, I will take vector int colon colon iterator. Vector has an iterator by the type name iterator. So I define that iterator P, and why do the find? Because I have to finally get that iterator. Now, how do I get the first iterator? So vector iterator has a method begin, which positions me on the beginning of the vector. And it has another method end, which positions me one beyond the last element of the vector. So this is the first, this is the last, and X is the element that I'm trying to find. So it does this process and it finds or does not find. If it finds, then what will happen? The value returned, the iterator value returned will be equal to the end. So if P is not equal to V dot end, then we have found X. If it is equal, then we have exhausted, we did not find X, right? So this is the way to write, I mean, lifting the find process and writing it for type, any type of container. So couple of examples to show you how common the code is. So I have a vector of int. This is the code that will work. I have a list of string. The data structure is different. The element type is also different. But again, conceptually, the same things are there. The list has an iterator type, and it has a begin method. It has an end method. So this is a uniformity which is created across the containers. And it iterates according to the algorithm find that we have just discussed. And when it terminates, I check whether P is equal to V dot end or not. If it is not equal, we have found X. Otherwise, it is not there. The third is a set of doubles, something very, very different. Again, the same code will work. So you can see that a find algorithm, which to be able to write, you needed to know the element type, you needed to know the container type, and write a specific code for each, will now get generated automatically through this lifted algorithm. And everything has become, I mean, kind of the same code, except for the instantiation of the type of container that, so this particular part answers the two basic information that influence the writing of the actual code, that is, what is the container and what is the type of the element. So you write the container and the type of the element. Rest of it is all uniform. So that's the beauty of STL. That's the beauty of generic programming. So this is how you generically can find, because whenever you kind of the begin equals the end, you know that your search has been unsuccessful. So end is one element beyond the last element, simply to also to take care of the fact that you can, otherwise you cannot represent an empty sequence, right? Because an empty sequence does not have a last element. So I mean, if you represent an empty sequence, then what you'll have is begin and end both point to one beyond the last element, which says that there is no begin, so there is no sequence as such. Right? Another simple algorithm, say find if. That is here, earlier we were finding an element. Now we are finding an element which satisfies certain condition. So if is that condition. So we have another template function, find if, two iterators, and then we have what we pass is a predicate. That is basically a logic which say whether the element satisfies the condition or not. So I want to find if this vector of integers have an odd number. So I do begin end, and I do odd, which is a predicate. You can pretty well now know that odd could be a function object or a functor, which checks for oddness. So given this find if, you can see that change here. Earlier we were checking not of star first equal to val. Now you are checking that if I pass this element star first, which is the current element, to that predicate, whether the predicate is satisfied or not, right? So you pass this functor. So let us go to the next slide and see that functor. So it could be either a function like odd int I, which returns this. Is it 7 or no? Is 7 odd or not? Or it could be a function object like this, where I overload the function call operator the way I've shown yesterday and returns this. So you can pass either of that. That's also a beauty of the STL algorithms, that almost in every case where you need to abstract a policy, a condition to the algorithm, you can pass either a function pointer or a function directly or a function object. Certainly, if you need to have state, you will have to pass function objects. So this is another example this is a functor with a state, a less than functor, which checks if the given value is less than a stored value. So when you instantiate this functor, you pass a value which is stored in its state, and you keep on checking if it is less than this value 43, or you instantiate it with a value perfection. So basically this was it is a templatized functor. So this was a functor for instantiated for integer. If I write less than perfection, then I'm certainly looking over a list of string components, string elements, and this will be instantiated. The functor less than will be instantiated as a functor of working on strings, right? So beautiful uniformity in the code that you can see here, and extremely compact code that you can write. Function objects are incidentally very efficient. They're easy to inline. They're faster than equivalent functions usually. I mean, that's a basic beauty. No, forget about all those details. So what we need is to have a useful algorithm. You eventually want to parameterize by a policy. For example, for sort, the policy is comparison criteria, right? Because given that policy of how to compare, rest of the sort is same for everything, right? So for example, here, I'm trying to do this on a record. We're trying to do this on a record, which is got a string type name component and a character array type address component. So I can sort by name by giving sort algorithm a policy which is comparing names. Or I can sort them by address by giving them a policy which is sorting by address. So the policy is important for these algorithms. So this is the compare by name functor. We just compare strings. And this is the compare by address functor, which uses the C string library strncmp to compare the two arrays of addresses. Right? And then everything else, once you have given the policy for your case to the algorithm, rest of the algorithm is all uniform. So I mean, we haven't looked at this, but often what happens is you can also write the functor in the lambda notation. This is called the lambda notation. Lambdas are nothing but they are kind of functions without a name. So you are just in C2 writing everything, the parameter list, parameter type, and the function body together, and this pair of square brackets denote that it's a lambda. So lambda is a special type of a functor. There are a lot of things in terms of lambda. We are not getting into that. But if your policy is simple, then you could just write it in C2 in terms of lambda, which makes your code even more simple and explicit. So to use otherwise, since you have not gone into lambdas yet, you can just write the functor and use that as a policy. So a little bit of look into vector, which is the most common container. So class vector is of an element type T, and so this is the value type. The actual iterator type has details, but what is important for us to know that there is a method begin, which is a method of the vector, which returns to the iterator positioned at the beginning of the vector. Similarly, there is an end method which positions you one beyond the last element in the vector. There are constant versions of these iterator. You can see these are const member functions. These constant versions are required if you are using a constant vector. Now, if the vector object is constant, naturally you cannot invoke begin or end because those are non-constant member functions. So there is always an iterator type and a const iterator type. So const iterator type would never change anything in the element. So at times for certain data structures and algorithms, const iterator will have a limited functionality than the iterator. Then you can do erase. Then you have a method to erase. So you pass an iterator to the erase method, and that element gets erased, and you are returned the next element after the. So you get back the iterator, which is the next element. Or you can insert at a given point, pass an iterator and a value. It will be inserted before this current element. Right. So this is kind of the vector that you have. And so this is the insert operation in a vector. I have a current vector here. I started with P being V dot begin. So initially I was pointing here. I have incremented it thrice. So I pointed 1 increment, 2 increment, 3 increment. So this is where P is. Then I created iterator Q with this value of P. So Q was pointing to 3 as well. Incremented Q. So this is where it points now. Now, if I insert P99, then at this current position, 99 will get inserted and P will point to that. But it is important to note that Q gets invalidated. Because you have inserted in a vector, the elements move. So wherever Q was pointing to earlier is not the same position anymore. So while P remains valid after insert, Q gets invalidated. Next slide, 34. Similar to insert, you could do erase. So if you do erase P, then this element will be removed. And again, other elements will be moved. P will point to the next element, but Q gets invalidated. This is the property of the methods in vector. Similarly, another container list, which is again, you can see this uniformity. This uniformity is what is important for the STL, because you are trying to write algorithms generically without getting into them. So every container has an iterator, has a const iterator, has begin, has end for both, has an erase, has a insert, though the actual behavior could depend based on the container type. In slide 36, if I do the same code on list now, the same set of values, I started here with v dot begin. I have done plus plus 3 times, so I'm now pointing to 3. Q was set with P here and incremented, so Q points here. Now I do insert P99, so so 99 gets inserted, P points to it. But elements do not move in a list. In a vector, the elements have to move because they are contiguous. But in a list, elements do not move. So this is, I just wanted to highlight that difference, that When you do insert in a vector, your other pointer q was getting invalidated, but when you do that in a list, it will not become invalidated. It remains correct because elements have not moved. Similarly, you can do an erase. I will skip that. So given this, there could be several ways you can traverse a vector. You can just traverse it by size, which is naturally not a very flexible way of doing it. You could do it by the size type, accessing with doing something with VI. But what is better is you do it with the iterator, so that this code is actually reusable for any other container type when you change the vector here. Right? So whereas if you wrote it using the first two styles, you can use it only for the vector, but not for anything else, because VI, things like VI is not available in list because it's not an indexed data structure, or it's not available in set because it's not an indexed data structure. So this is you can do this, which is what we have seen. You could also do a complete range, right? If there are many things you need to do till the end. So this is what you're doing, begin to end for the entire range. So you can write it very simply as vector t colon value type. You saw the value type is defined, which basically will be the type of value that v keeps. So colon value type t in vector v. So you don't have to even write this begin end, because you are doing it for the whole range. Then as this iteration go through, you keep on getting one element after the next. If you have the ability to use auto, which is automatic deduction of type, which your C++11 has, then you do not even have to write this. From the type of the vector v, it knows the element type and it can reduce this whole expression. So you can see how fast things are getting factored out and lifted and compacted together. So between the two, vector and list, naturally you should always use vector unless you have a specific reason to use list. You can grow a vector, unlike an array, traditional array. You can use pushback. Pushback is putting an element beyond the last element, right? And it does not, I mean, if it needs to resize the allocation, it will do resize the allocation and take care of that. Compiler takes care of the whole of those stuff. You can insert, erase in a vector and do everything. But the only key factor is, if you do insert erase kind of things in a vector, then the elements move. So you would like to, use a list if you do not want that kind of a movement to happen. And there are more containers like map. So these are some of the standard headers in STL, where functional has different function objects. Algorithm has different algorithms. IOStream, FStream, numeric has a number of numerical algorithms. Then string, vector, map is basically for creating a hash table, particularly in the assignment 3-4, you should be using map quite heavily, because you'll have to find out, given the station, you'll have to find out the distance between a pair of stations and so on. So these are good examples for that. Then you can have set and so on. I'll not go through the second part of this presentation. I think given the initiation that we have done, you should be able to go through that yourself and understand and learn about STL. Just just tell yourself one thing, that if you are going to become an efficient software engineer, then an efficient developer, then it's very important to understand the concept of generic programming and C++ STL. is the best place to gain that. So in the assignment 3 and more specifically in assignment 4 that is coming, I would expect that you will heavily use STL and write very compact code, not you know 2000 lines of code to do something, but you should be able to write that in 500 lines now using the STL and the templates. Okay, so we have had a fairly long discussion on the programming language vehicle, because certainly I do not look at C++ merely as a programming language. I look at it as a tool. I look at it as a way to learn the good design principles and good techniques. So I think this introduction to C++ would stand you in good stead in that way. If there are any questions, I would like to take that. Early morning, you people do not ask questions at all. I don't know why, but at least okay. Some of you send mails, which is good. Keep on doing that. I got a very interesting mail from Mr. Onimesh Jha yesterday, asking about what is the difference between a functor and lambda expressions. So thank you, Animesh, for asking that question.
Excuse me, sir.
Yes, please.
Could you tell us what the syllabus for Wednesday's classes, like Wednesday's class
For
test?
for for I mean whatever we have done till now.
So
C++.
till today's class as well.
Till today's class. Yeah, yeah. Till
Could
today's
you?
class, this presentation will be uploaded right now.
Okay, okay, sir. Thank
Okay,
you.
obviously, all this presentation, the functor presentation, then some presentation I have updated, like use of exceptions and so on. So all those will be sent right across.
Okay, sir. Thank you.
So, if we
Yeah.
pass a functor object with the, with whose operator has the wrong number of arguments, like we expect one argument, we give two or something like that, then
Mhm.
like how does the compiler actually understand or constrain that? Because in the template signature, there's no way to tell that.
In the template, no, in the template. Oh no, that is okay. That's a good question. So behind each one of these, there are traits information, right? So the trait will tell you that what kind of a functor you will have to pass, right? So, for example, we have seen the comparison policy for sort, right?
Yes, sir.
So actually, I have annotated that also in the slide now. In the functor slide, you'll see. But what that expects is that you will send a functor which takes two components, two elements of the same type and returns a bool. This is a trait, right? So if you violate that trait, then naturally compiler will expand out the template code into the actual code, and then it will not be able to compile because that function call mismatch will happen. Compiler does not have a problem. The problem is with the developer, right? That you have to know that when you pass a functor to sort, you must pass a binary function of two same types of elements and return type is bool. So to ease that, the functional component is given, where even the binary function signature is being given. So you are supposed to specialize from that. But
Okay, sir.
even
Got
in
it.
that, instead of writing double bool, you write double string bool. Nobody can stop you from doing that. But if you do that, then it will not compile, because
And you get a
simply
2000 line error message.
yes, you get 2000 line error message. I mean that I think is a very irritating area of this STL is, if you have an error, the compiler naturally has to tell you a lot of things. So
Yeah,
it
like
takes a
in
little
some
bit.
other languages, probably Rust or Haskell, I get very much nicer error message. Like if I when I try to put something wrong, the compiler tells me that look, this is the wrong signature and you can't do this. But
Ab-
here,
a- Absolutely, I would fully agree with you. I'd fully agree with you.
it
But
was nuts.
is the bulk of the compiler, and a lot of the compiler code is again reused. So there are a lot of legacy issues. It's not easy to change a language which is evolving for 35 years, 40 years almost.
I used to wonder why
Oh,
this happened, but okay. Thank you, sir.
historical, significantly historical, I would say. But there is
Okay.
there is a lot of effort in C++ 23 that will come in 23 to improve this messaging significantly. But that means a big rewrite for the compilers, which is a very difficult task as to who is going to, because checking a compiler is a big job. Anyway, we are completely out of time. See you then on next Wednesday. I will send out these presentations, and be ready for the test in the Wednesday second half. In the morning class, we will have, as usual, we will start talking about software development lifecycle and other aspects of software engineering. Thank you very much. Have a nice day. Bye.